Hi, my name is Kanaria Teet, and I'm an assistant professor in the Graduate School of Education at the University of California, Riverside.
Hi, this is Li Ye. I'm an assistant professor in the Department of Chemistry and Biochemistry at Cal State Northridge.
Hi, my name is Jack Eichler. I'm an associate professor of teaching and chemistry at the University of California, Riverside.
Hi, my name is Matt Castleman. I'm assistant professor of teaching in chemistry at UC Riverside.
More than 1/3 of all students will take at least one online course during their post-secondary education. Utilizing effective online learning tools, particularly in science, tech, engineering, and math fields, is of the utmost importance. It is well known that students in STEM fields have lower rates of retention in their major, and this is compounded for underrepresented minorities. Introductory or gatekeeper courses are often barriers to advancement within STEM majors. Thus, understanding how online learning tools can be developed and adapted to improve educational outcomes in introductory physical science courses is imperative to reduce attrition from STEM majors, especially for underrepresented minority students.
From past research studies, we already know that students learn better from words combined with pictures than words alone. This is particularly true in learning chemistry because understanding of molecular phenomenon exists at three levels. The first level is microscopic level, since that they can be directly observed by students through their eyes. The second level is submicroscopic level, structures of atoms and molecules. The third level is symbolic level, chemical and mathematical formula. Students experience the world around them at the microscopic level, but introductory chemistry is largely taught at the submicroscopic and symbolic level. Therefore, integrating and relating the three levels is very important for students to understand chemistry.
Online simulations are beginning to find wider use in chemistry classrooms to support traditional instruction. These learning tools are digital environments where students can interact with models that simulate both large-scale observable phenomena and submicroscopic chemical changes. Simulations are typically interactive and allow students to manipulate parameters and make observations about the resultant changes. Despite the growing use of simulations, there is no systematic research that has examined how students' learning needs are met by this type of intervention.
As part of our project, we will design and evaluate the effectiveness of online formative assessments and online feedback as support for student learning using virtual simulations. Formative assessments are assessments used during the learning process to provide feedback for students and instructors so that they can act upon the feedback to improve learning and teaching. Our hypothesis is that students who can complete the online formative assessments and receive online individualized feedback while using simulations will demonstrate equivalent understanding to students who complete the formative assessments but receive generalized feedback similar to what students receive in a traditional lecture. And both will perform better than students who do not use the simulations but complete more traditional classroom activities.
Our study will probe the effectiveness of simulations with online formative assessment and feedback for two different subject areas in introductory general chemistry. Participants will be split into three treatment groups. In the first group, students will complete an online simulation activity and then take a formative assessment to assess their learning. The formative assessment in this group will provide individualized feedback for each student answer. In the second group, students will complete the same online simulation activity and formative assessment, however, only receive generalized feedback based on their formative assessment scores. In the last group, the students will attend a synchronous online lecture, take the same formative assessment, and receive generalized feedback on their answers. To measure learning gains, all students will take a pre-test prior to completing the online simulation and a post-test after completion.
At the conclusion of this study, it is our expectation that we will distinguish if integrating online formative assessments with online feedback into simulation activities is effective at improving student learning about molecular structures and their properties. Understanding how different learning scaffolds affect student learning will allow us to design more effective online learning environments, particularly those that can serve all students with a variety of cognitive skill sets and learning needs.